Okay, so in this lesson we're going to look at solving exponential and logarithmic equations. Really we're only solving exponential and we're using logs to do that. So exponential equations are equations in which the variable appears in the exponent. The following are examples. So we've got 7 to the x equals to 7. In this case, x would have to be equal to 1, otherwise 7 wouldn't equal 7. This one we've got 3 to the x plus 1 equals 9. Just from common knowledge, right? We know that 3 squared is equal to 9, so x would have to be equal to 1. This one's a little bit trickier, right? We can't really solve it by what we would call inspection, just looking at it. But we'll talk about how we can solve this, okay? So there's 3 different ways how we're going to do this. So equations where the bases are equal, that's our easiest one. That's what we're going to start with. Equations in which the base are not equal, but we can get them to be equal. And then equations that require a log to solve. Okay, so those are kind of our 3 things that we're going to look at. So if we're looking at where the bases are equal, basically what happens here is if we have some base with some exponent equals to the same base with a different exponent, then those 2 exponents have to equal each other. Otherwise, the left side and the right side of the equation are not going to equal each other. Okay. That's true as long as the base is not 0 or 1, because like 1 squared is the same as 1 cubed, right? So that's the only case where it wouldn't work. Or 0 squared is the same as 0 to the 4. So as long as it's not that, right, 2 to the 1, the only way that we can get that to be equal is if we have the same exponents. So for this one, we have 3 to the 2x equals 3 to the 4. So what we know is that these 2 exponents have to equal each other. So we can just write 2x is equal to 4. Then we just solve for x. So x would be equal to 2 for that to be true. This one, again, we've got same bases. So 4 to the 2x plus 5 equals 4 to the x plus 1. That means the 2x plus 5 has to equal the x plus 1. And then we solve for x. So I'm going to subtract x from both sides. So 2x minus x is just x. And then I'm going to subtract 5 from both sides, so I get x is equal to negative 4. And then this one, we've got 1/8 as our base, but they're equal, so it looks a little bit more complicated, but they're still the same base. So the process is still the same. We say the exponent on the left side, oops, should not be an equal sign. So the exponent on the left side has to equal the exponent on the right side. If we add 1 to both sides, we get that exponent has to be, or that x has to be a 10 in order for those 2 things to match. So that's kind of our first case. The second case is when the bases are not equal, but we can manipulate the equations to make the bases equal. So something like 8 is equal to 2 cubed. Okay, so there's situations where we can look at the bases and say, okay, I could represent both of these bases as the same base power, and then my bases are going to be the same. So if I have 2 to the 3x equals 16 to the x minus 1, the first thing that I need to look at here is that these are both multiples of 2, right? Or they're both like powers of 2, right? 2 to the 1 is 2, and then 2 to the 4 is 16. So I could replace this 16 with 2 to the exponent 4, and that whole thing is still raised to the x minus 1. Okay, so now I'm on my way to having matching bases. Before I can equate my 2 exponents, I need to simplify this guy. So I need to distribute this 4 onto the x minus 1. Because remember, when you've got an exponent raised to another exponent, we multiply them. So this is going to be 2 to the 3x equals 2 to the 4x minus 4. Okay, so now, because I have one base with one big exponent equals one base with another big exponent, now we can equate these two. So it's going to be 3x is equal to 4x minus 4. So if I subtract 4x from both sides, I'm going to get negative x equals negative 4. Divide both sides by negative 1. X is equal to 4. Okay, so same process as before, but we needed to we needed to multiply that, or sorry, manipulate that base. Okay, so this next one, again, we've got 9 and 27. Those are both, if we think about 3 to the 1, that's 3, 3 squared is 9, 3 cubed is 27. So we can get to both of those numbers by a base 3 power. Okay, so we're going to replace both of those with their corresponding base 3. So 9 is 3 squared, and then that whole thing is still raised to the 2x minus 3. And then 27 is 3 cubed, and that whole thing is still raised to the x plus 4. So before we can equate these two exponents, we need to simplify them. So 2 times 2x, so this is 3 to the 4x minus 6, and 3 to the 3x plus 12. So then we equate these two exponents. So 4x minus 6 is equal to 3x plus 12. So if I subtract 3x from both sides, then I get just x over here. If I add 6 to both sides, then I get 18. So for this to be true, my x needs to be 18. This last one's a little bit trickier, so we've got 125 and 1 over 25, okay? So what I notice about both of these right now, or right away, is that they're both multiples of 5, right? So my best guess for what power these are 5s. So if you think about 5 to the 1 is 5, 5 squared is 25, 5 cubed is 125, okay? So this 125, that can be replaced with 5 cubed. This 1 over 25 is the same thing as, so remember how we talked about if we did like if we had a negative exponent, it's the same as, so like n to the negative 2, that's the same as 1 over n to the positive 2. So how this 25 could have gotten on the bottom is if it was 5 to the negative 2, because that would have been the same as 1 over 5 to the positive 2, which is 1 over 5 squared is 25. So this 1 over 25 is 5 to the negative 2. And then it's all raised to an x plus 9. So at this point, again, we need to multiply this in to simplify first before we can equate the two exponents. So it's going to be 5 to the negative 2x plus, or minus 18. So that means that 3 is equal to negative 2x minus 18. To get the x's by itself, I'm going to add 18 to both sides. So I'm going to get 21 is equal to negative 2x. So then x is equal to, I'm going to write the negative up on top, so I need a little bit more space. Negative 21 over 2. Okay, so they're not always super nice numbers, and that's okay. And then to check this, you could actually plug that in for the x and see if these two numbers are equal to each other. Okay. Our last case is when the bases cannot be written as powers of whole numbers. Okay, so we can't get the base to the same thing. In this case, we need to use a logarithm. So there's kind of two ways that we can do this. So the first way is that we can turn this thing from exponential form. So we can change exponential form into logarithmic form. Okay, so basically the conditions for that is that you need something like a to the x equals y. So it's got to be one concise, there's one exponent, there's one answer to said exponent, and then we change that into, So remember, a log is log, this base is going to be the same of, so we're talking about what exponent, that's always going to be the answer, right? What exponent do we need to raise this to get from the base a to whatever y is, right? What exponent do we need to raise the base to get to y, okay? So we would change from one exponent to the log. The other option, because we can't always get it to look like this, is to log both sides. Okay, so we're going to go through both of those examples. This one's a little bit more rare, this one's a little bit more common, so there's more of these examples. So this first example, we've got 80 to the 2x minus 4 equals 5. And so if I want to get x by itself, the first thing that I'm going to do is move the 4 over. So I'm going to have 80 to the 2x equals 9. So that makes it a little bit simpler. Now what we have is something that looks like this, right? We have a base with one exponent equal to one other number, so we're going to change this to log form. It's going to be log of base 80. And so remember that whatever the exponent is equal to, right? So the 9 here, that's going to become the argument of the log. So 9 is equal to 2x, right? So we're just switching from exponential form into log form. And again, if you ever get confused, you can write out kind of an easy one to say, okay, I know where things go, right? 2 to the 3 equals 8, 2 to the 3 equals 8, okay? 80 to the 2x is going to equal 9. We just don't know what 2x is. Okay, to figure out what x is, we're going to divide both sides by 2, and x is going to be equal to log base 80 of 9 divided by 2. And that's actually as simple as it's going to get. So we want to leave these things in what we call exact values. So this is an exact value. It's on a rounded decimal as often as we can. So it's tempting to punch that into a calculator, but this is actually how we prefer to see these written, is still in log form, okay? This one, we can't get this to just one exponent. So see how we've got 1.5 to the x equals 4 to the x? In this case, what we're going to have to do is log both sides. And whenever you're going to do this, I would say just use the common log, right? So base 10. That way you don't have to write a base. So when we log both sides, it's kind of like square rooting both sides of an equation. So yeah, this one we can't convert it to just one log because it's not, there's exponents on both, and then we don't know how to do that, okay? So what we're going to do is we're going to log both sides. We're going to use that common base because it's kind of like square rooting, right? So what we do to one side, we're going to do the other. So we're going to log 1.5 to the x, and we're going to log 4 to the x. And then we're going to use our log rules to get x by itself on one side of the equation. Generally what that means, so when x is the exponent, that's why we're going to log it, because that exponent, based on our rules from yesterday, can come down in front. So it's going to be x log 1.5 equals x log 4. Okay, now to get x by itself on one side of the equation, we're going to need to subtract this from the other side. So x log 1.5 minus x log 4 is equal to 0. And then we need to factor out an x so we can divide everything else out. So it's going to be x times log 1.5 minus log 4. So we've pulled out that common factor of the x. Now what we're going to do is divide by what was left over. So log 1.5 divided by log 4. What we do to one side, we must do to the other. So 0 divided by anything, doesn't matter, is still just 0. So these guys are going to cancel. We're going to just be left with x is equal to 0, because 0 divided by anything is still 0. And if we think about it, that makes sense, right? Because 1.5 to the 0 is 1, and 4 to the 0 is 1. That's the only way that those things can equate. Okay, so we might have just gotten there right away and said like, well, logically, then x is equal to 1. But this is kind of how we solve it. So we're going to do that again for another example. So I've got 6 to the x minus 2 and 4 to the negative 2x. So this one we can't get these to the same base, right? 4 could be represented as 2 squared, but 6 can't be represented as a base 2 power. So we're going to have to log both sides again. So we're going to log 6 to the x minus 2, and we're going to log 4 to the negative 2x. Okay, and whether you choose to do brackets on logs or not, it actually most of the time doesn't matter unless you've got multiple terms being logged. So this one, it's kind of all one deal. We don't need the brackets there. The beauty of doing a log, why we do a log, is that that x, or that exponent with that x, can come down in front. So it's going to be x minus 2 as a package deal times log 6 equals negative 2x times log 4. Okay, so when we need to get our x's on one side of the equation, first thing that we need to do here is multiply this log 6 into these brackets. This is going to be x log 6 minus 2 log 6 is equal to 2x log 4. And then again, like we did up here, we need to move the x's to the same side so we can factor them out, pull that x out by itself. So if I subtract the x log 6 from both sides, what I have left is 2 log 6 equals negative 2x log 4 minus x log 6. From that side, I then need to pull out that x. So we just have negative 2 log 4 left in that first term and negative log 6 left in that second term. And that's still equal to negative 2 log 6. To get x by itself, we're going to divide by this whole dealio. We're going to cancel from this side. So then what we're going to have is x is equal to negative 2 log 6 over negative 2 log 4 minus log 6. Okay, and one thing that would clean this up a little bit is dividing each term by a negative 1. Okay, so this divided by a negative 1, this divided by a negative 1, this divided by a negative 1. That would make all of those terms positive. If you didn't do that though, like that wouldn't be a big loss of marks or anything. That just cleans it up a little bit. Okay, so there's our answer there. And again, it's in exact values. We don't want to get rid of the logs. We don't want to punch this into our calculator or anything. Our last example, and this is a little kind of clustered now, but that's okay. So same deal, we've got 5 to the x minus 3 and 2 to the x. We can't get those to the same base. What we're going to do is we're going to log both sides. Okay, so we're logging both sides because it's kind of like square rooting both sides. What we do to one side, we can do to the other, and then we can apply our log rules. So that x minus 3 is going to come down, and that needs to be in brackets so that both terms get multiplied with the x, or the log 5. And then the x is going to come down and multiply that log 2. And then once we get to this point, it's actually a really, really repetitive process. So we're going to factor this guy in. It's going to be x log 5 minus 3 log 5 is equal to x log 2. I need to get both of my x's on one side of the equation, so I'm going to subtract this from both sides. That's going to be x log 2 minus x log 5. I'm going to factor out my x. Then divide both sides by that. That's going to cancel there. And then we've got x is equal to negative 3 log 5 over log 2 minus log 5. Okay, so in these equations, you're generally going to have logs left, okay? The only one that wasn't true is this x equals 0 case. That's a little bit unique. Every other one, it's going to be in this kind of big, it looks really complicated. It looks like a ridiculous number, but we could just figure out a decimal for it. Okay, so that would work. The other way to check this, to check if you've done it, is graph these two lines, find their point of intersection. Does that x decimal match this one? Okay, so that's a way that you can check whether or not you've got the right answer. Okay, so there's more examples in your snap book if you want to look at a couple more. Or you can ask me any questions you have about it, but you should be moving on to do some practice now. Okay,